Okay, let's get started. So next week will be our first exam. Cover everything from the beginning of the semester through whatever we get through today. On this slide, I've listed the major topics we've covered so far. So you will have a couple of conversion questions, but I'm not going to spend a lot of time asking you about that since all of you have now passed your exam. But there will be a couple of them on there. We'll go through some of the properties of water. All of the properties are fair game for the exam, but the ones I emphasized most were how to read the phase diagram for water, where dipoles come from, how they originate in molecules, and the effect that they have on the properties of water. We talked about the generation of hydrostatic pressure and how to calculate it, depth times density times gravity. And then we spent a fair bit of time talking about the energy requirements, getting water to change temperature and change state. Remember, it requires 1 calorie per degree per gram of water to raise the temperature. But then when you change phase, you have to either add in latent heat of fusion, if you're going from a solid to a liquid, or latent heat of vaporization, if you're going from a liquid to a solid. If you're going the opposite way, cooling things off, those latent heat values are added to the environment and lost from the water as it goes through those transitions. We went through basic groundwater terminology, saturated zone, unsaturated zone, water table. Remember, in water table aquifers, the water table mimics the Earth's surface generally. We talked about different types of aquifers: confined, unconfined, water table aquifers, perched aquifers, alluvial aquifers, artesian wells, and flowing wells. So know what those are. We spent a bit of time talking about relationships between groundwater and surface water, differences between gaining and losing streams. But we spent a fair bit of time the last 2 weeks talking about base flow recessions, how to calculate what stream flow should be at various points after a recession begins. We're going to continue on with that a little bit tonight and look at recharge. So the stuff I have listed on this slide in red are topics that I'm hoping to get through tonight. I don't know if I'll get through both of them. If I don't get through both of them, they obviously won't be on the exam. And we spent a little time with the hydrologic equation last week. I gave you a problem that was somewhat difficult. I put another one on the website last week. I don't know how many of you have had a chance to work through that, but I put the problem and a solution up for you. And if I get a chance, I'll try to put another one up this weekend for you to practice with. Now, the one thing everybody always asks me about the exams is, do we have to memorize the equations? Yes and no. I'm going to put the equations on the exam, but I'm not going to define them. I'm not going to tell you what the variables are. So you kind of have to know them, you know. But I'll have just the general equation up, like for base flow recession, Q equals Q naught e to the negative KT. That's all I'm going to put up there, okay? You got to know what all the variables are in order to use the equation. So do you have to memorize it? No. Do you have to know it? Yeah. So I think you guys can get the point. If you're a graduate student, I'm going to have a couple of questions that are a little more difficult for you. I have to prove to the university that you are doing something above and beyond what the undergraduates are doing to get your graduate credit. And the one thing I said I would do is I'd give you a little more difficult exam. So if you're a grad student, a couple of the problems will be a little more involved. If you are taking the exam online, I will send you a Zoom link before the exam. Once you log in and I can see your face, I will email you the exam. You're to use no outside sources. So that means once you start the exam online, I should not see you typing and mouse clicking. And if I do, I'm going to be very upset, because all you need to do is write your answers down on a sheet of paper, take a photo of those answers, and email it back to me at the end. So the only time you should be actually on the internet and typing and sending me stuff, if you're doing this online, is at the very end when you're emailing me this material back. You all have the option of taking it at home or here. Doesn't matter to me where you do it, but I expect you to do it fairly. Do any of you have any questions? If you do, I've got email all week. I should be able to answer your questions. But like I said, anything's fair game, but I will try to stick to topics and concepts that I spent a fair bit of time in class talking about and emphasizing. Okay? All right, if there are no questions, let's move forward with this. I always like to start with a little review of things that we covered in the previous class. So last class we were talking about base flow recessions. So let's just draw out a hydrograph here. And it's going to go full year. It's going to go from January through the end of December. So this axis here is time. This axis here is this is discharge. It can either be cubic feet per second or cubic meters per second, whatever the unit happens to be. A typical year hydrograph might look something like this. Okay. Now, a way to think about this is that this period right here, once the water levels start rising during the spring melt, this is a time where we are recharging our aquifer. Because remember, during this last part of the year, as the stream flows tail off, this is our base flow recession. And remember, base flow is water that's coming from the alluvial aquifers, and it's pouring into the stream. So from January through, whether that's April 1st, May 1st, June 1st, whenever it starts to tail off, that's a period where those alluvial aquifers are going to recharge as the water levels in the stream rise. And that's what's shown in the black line here. From January onward, you see it gradually rising. As it rises, some water from the stream filters back into the aquifer, raises the water table in the alluvial aquifer. At some point we peak in our stream flow. That's our Q naught. That's the stream flow at the start of the base flow recession. And after that Q naught, you see a gradual tailing off of the stream flow as water that was recharged earlier in the year is now released back to the stream as stream levels drop. And remember, we can sort of estimate what the stream flow is going to be at any time after the start of a recession with our base flow recession equation. So the discharge Q at any time after the start of the recession equals the discharge at the beginning of the recession, Q naught, kind of that peak flow. And it's e to the negative kt, where again k is unique to each watershed. And T is the time after the start of the recession. And I've given you a few sample questions over the last couple weeks. You've had a chance to work this forwards and backwards. And hopefully you are at a point now where you understand this, okay? And I mentioned this to the in-class people, that I didn't mention it to the online people, and that's because Keaton asked me a question at the end of one of the classes about the mathematics of this line, this Q equals Q to the negative KT. Now this class we don't require calculus, but if you've had calculus, you know that if you integrate an equation, it's basically shows you the material that is beneath a curve. So in this case, let me see if I can use this here. You have this equation that defines this line. It's a best fit line for the base flow recession. Now, if you think about it though, all of this material underneath that curve, that means something. What that actually means is so you have Q. Let's just say it is in meters cubed per second. And you have time. If you multiply meters cubed per second by time, let's say in seconds, what do you get? Meters cubed per second times seconds. Seconds cancel out, right? You're left with meters cubed. This is the volume of water that's input to the stream during the recession. This base flow recession equation gives you a Q, right? That's the stream flow. That's how fast the stream is moving. That's how much flow is in the stream at any time after the start. But sometimes it's useful to have a way to calculate volumes. I've used this example before. If you're managing a dam, it would be nice to know the total amount of water that would be expected to flow into your dam during that time period. Now we could use calc to do this and integrate this equation, but you guys, some of you have had calc, some of you don't, some of you have had calc and hate integrals. Whatever, we're not going to use calc in here. So it's helpful if we have a method for doing that without using calc, and we do. So we actually have what we call an empirical method for calculating the total volume of water released during a base flow recession. And it's a really simple equation, actually. And I'll just put it up here. Okay, so there's your equation. VTP equals Q naught times T1 over 2.3. Let's just define some terms here. VTP, total volume of water that's input to a stream during a recession. As I said before, that can be something that's really useful if you're managing a dam or if you're managing a groundwater system too. It's nice to know how much water is going into your aquifer, how much water is going out of your aquifer, how much water is available for use. All right, I'm going to flip this over to the next slide and rewrite the equation back up. Let's do that again. VTP equals Q naught T1 over 2.3. Again, VTP, total volume input during a recession. So again, let me put this plot up that we had earlier. Here's Q, here's T, here's our hydrograph. Q naught is the flow at the start of the recession. And what this equation is going to tell us is the total volume, again VTP, input to a stream from the groundwater system. During a recession. So there's several ways we can use this. We're going to use it in a specific way here in a minute. One variable I haven't defined is this T1, Ti, I guess we can call it. And again, I said this was an empirical equation. You guys know what empirical equations are? You may have heard the term before. It's a term that defines an equation that's originated by trial and error. It works. You see this 2.3? It's 2.3 because 2.3 works. It's not that it was derived from anything. This is just an equation that gives us an answer that works. A lot of times it's done by trial and error. It wasn't derived from some other equation out there. This is just what we call empirical. Again, and I'll just write it down. Empirical equations are developed generally through trial and error. If we want it super precise, we can take that base flow recession equation and we can integrate it and we can throw some calc at it and maybe get a slightly better answer, but this works and it's simple. It's actually really simple. T1 or Ti, however you choose to read it here, is simply the time it takes for Q to drop from the initial Q So the Q at the start of the base flow equation, base flow recession, to 1/10 of that amount. Probably makes no sense at all. Let me give you an example. If Q naught equals 2,000, let's use meters cubed per second. And T1 is the time needed for Q to drop to 1/10 of that. In this case, 200 meters cubed per second. My guess is at this point none of this makes any sense. So let's do a problem that hopefully will illustrate it. Okay? You guys have your notes? Need another sec? All right. Let's put up that equation. VTP. Total volume of water released to a stream from the alluvial aquifers during a base flow recession. Okay? Q naught, Q1 over 2.3. Write that better. Okay, let's say the discharge at the start of a base flow recession was 1,100 meters cubed per second. Okay? This would actually be a pretty big stream to have that sort of discharge. Again, TI is the time to 1/10 of Q naught. In other words, time it takes for the stream flow to drop 210 cubic meters per second, 1/10 of Q naught. And for this example, let's say it's 7 months. To make the math easier, we'll just use 210 days. So the question would be then, is what is the total volume of water that is released by these alluvial aquifers and in this case we'll just make it a 7-month recession, same length of time that it takes for that stream flow to drop to 1/10 of its original value. Now sometimes recessions will go longer. Some years are a little drier, drags on a little longer before stream flow kicks back up. It could be 8 months, it could be 6 months, it could be 9 months. I'm just using 7 months because I feel like it in this case. So let's calculate the total amount during a 7-month recession. So VTP equals Q naught, which is 1,100 meters cubed per second. Times 210 days. Over 2.3. But you can see right now, we've got meters per second times days. We want a volume So our time is going to have to cancel out. So we're going to have to convert days to seconds. So we have 24 hours in one day, 60 minutes in 1 hour, 60 seconds in 1 minute. Days cancel, hours cancel, minutes canceled. We're left with seconds. And depending how you round it, should be close to 8.7 times 10 to the 9th meters cubed of water. So that's actually a really useful value. It tells you how much water moved from the groundwater system to the stream. So you know how much your groundwater aquifers lost, you know how much the stream gained, you know how much is moving downstream due to groundwater. If you're trying to quantify these different hydrologic systems, this is all really useful. So a way to think about that also is, let's say we have a stream. It's moving down. Here's the water level in the stream. At the start of the recession, where we had a stream flow of 1,100 meters cubed per second. So that's how much water's flowing in there. Over the next 7 months, that stream level is going to drop. And it's going to drop a lot. So now here is the level 7 months later. When Q is 1/10 of what the flow was at the start of the recession. So what that means is during that 7 months, water poured from the aquifer into the stream. And you can calculate the volume of water lost pretty easily. All right, any questions on how to do that? It's pretty simple. You just need two values. You need Q at the start of the base flow recession. Yeah?
So the 10-month period, it's just implied that that is the amount of time it took to get to 100%.
Okay, the what month period?
The 7 month.
7 month.
It just says during a 7-month recession.
Yeah, so in this case, this is the volume that comes out during a typical base flow recession. And if the typical recession is 7 months, then you use this value. So it's the amount of time it takes to drop from, in this case, 1,100 to 110. Sometimes they might go a little longer, and the water level will continue to drop. We have another equation coming up that tells you how to deal with some of those things. But for this one, it's just pretty simple. What's the length of an average recession? How much water comes out during that average recession? Okay? I'll try to give you another example or two where we can use... Yeah, go ahead.
Sorry, if the 7 months at the end of this question, 7 months, is that like a necessary part of the question? Like if that was different?
We're going to go to different in the next part.
Okay.
Okay, so this is just, if in this case, you only have two values.
Okay.
The Q naught at the start of the base flow recession, that's pretty easy to measure off of your hydrograph. And then you need to know the time it takes for the discharge in your stream to drop to 1/10 of that. When that happens, that's considered to be the total amount of volume released by these aquifers during that 7-month sort of average recession. Okay? But if it got short-circuited early, if it only dropped over 6 months, we'd have to adjust this. Okay? Let me give you an example here. I hope this helps answer the question. Okay, so another useful thing to calculate in this system, and I'll show you why it's useful to calculate this here in a minute. We're going to use the last equation and this equation in conjunction with one another. Okay, so this is the potential base flow that remains in the aquifer at some time after a recession begins. Okay, let me show you what I mean by this. Okay, here's our hydrograph for a year. We have the spring melt, water levels rise, and then we have this base flow recession, okay? What this equation is going to tell us is what volume of groundwater remains in the aquifer at any time after the start of a recession. In the previous example, we talked about how much water was released into the stream. This tells us how much remains behind, how much is available to be released at any point in time. So we could wonder about here. What is the volume at time 1? That's kind of sketchy. Let me rewrite that. You do it this way. All right, what's the volume at time 1? Or maybe we want to know what volume is left in the aquifer at time 2. Or volume at time 3. This equation's a little more involved, but it's still pretty simple to deal with. I'll just write it out and then we'll go through it. Okay, to use this equation, obviously you have to use the previous equation to get this VTP value. So let me give you a question that will hopefully put all this together. All right. What is the total volume of water remaining in the aquifer six months after the start of a recession with an initial discharge of 1,100 meters cubed per second and time to drop to 1/10 of that of 7 months. I'm going to give you a couple minutes to try to work through this. So if you notice, these two values right here, 7 months and 1,100, is what we used in the previous example. So you've already calculated this value from the previous slide. Which is 8.7 times 10 to the 9th cubic meters. So look at your equation first of all. VTP, okay? What units are we going to have for that? It's a volume, right? From the previous page, you can see that it was in meters cubed, okay? This VT right here is also a volume. We want it the same units, okay? So that means that if this is a volume, VTP, and VT is also a volume, that means that these units here have to cancel out. So T and TI need to be in the same units. They don't have to be in days. And all the other examples, I've converted it to days. But in this case, I gave you months. TI is 7 months, and T is 6 months. So you can just divide 6 by 7 for that. You don't have to change it to days. you guys come up same answer? How many of you completely understand the concept? You're totally good with the concept here. My guess is none of you are totally great with it, but it's making a little sense. So I'm going to try to give you one more scenario that where you can put everything together and answer a real question. Okay, so okay, yes.
So you have to do both of these. So in the first equation,
Yes.
the
Okay. So
V1 equals 7 months.
yes.
And then the recession was 7 months. So you have to do both of these if those aren't the same.
Let me show you how it's really used, okay? This is those values on their own, they can be somewhat useful, but used together, they can be really useful. So let me give you a question here that I hope will answer your question and some other questions as well. Okay, so here's a question for you. Let me give you I'm going to give you 2 years worth of data here, okay? So let's go from, let's say, January to the end of December. So to January again, here's year 2. So we're going to have 2 years of this. And no 2 years are exactly the same, okay? And that's what I'm going to show here. So this is a hydrograph for 2 years, okay? This is Q. This is time. All right, so let's all right. And let's sort of break this down. What's going on from here to here? Tell me what's going on out in nature. Anything that you would know just by looking at this plot. What's happening to your stream level? Stream flow. It's increasing, right? This is during the snowmelt. Stream's rising, right? It's getting up near, it might flood, might not flood. It's rising, right? Okay, so your stream level's going up. So let's just write that down. Stream flow up. What's happening to your aquifer? During that time period? Getting recharged, okay? So this is a period of recharge for your aquifer. All right? Now from this time period to this time period, let me move this. I'm going to put time here. So during this next time period, what's happening to your stream flow? Dropping, right? So stream flow is dropping. What's happening to your aquifer? It's draining, right? It's losing water into the stream, okay? So your aquifer drains. All right? From January through, let's say, this time period, stream flow is rising again. Okay? I'm just going to put stream up and recharge. And then during the rest of the year, we have stream flow, Q, discharge dropping, and the aquifer draining. Okay, that's what's happening out in nature, okay? One of the most useful things that we can do in groundwater is figure out how much recharge is occurring to an aquifer. If people are using that aquifer for water for homes, gardens, irrigation, whatever, it's useful to know how much recharge is occurring, because that's how much water is going to be available for people to use, okay? So let's look at this period of recharge right here, okay? How would you calculate that recharge using some of the equations we have now? Just take a second, look at the equations I gave you, and can you put the equations together in a way that would help calculate the recharge? So my question, I guess, is what is the volume of recharge between the end of the year one recession and the start of the year two recession? So I gave you a couple of equations. Can you put those together to figure out recharge? Keaton.
Could you assume that the Q naught is the same for...
They are not.
They're not. Oh,
They're not in this case. In fact, let's see, do I have some values I can put on these? I do. Okay. So the Q naught, let me make some room here. God dang it, stop it. Let's put this out here. So Q naught for year one, let's make this, to make it easier, 1,100 cubic meters per second. That's what we were using in all the previous examples. Okay, the Q naught for year two is going to be 1,500 meters cubed per second. A couple of things I need to give you for this. Recession one lasts 9 months. It's going to be a long one. Time it takes for Q to drop from 1,100 to 110 in the first year's recession is 7 months. Okay. Now, did you figure out how to put the equations together? You need to know how much water went back into your aquifer, right? Do you have an equation that tells you anything about the volume of water in aquifers? Which one?
VT is equal to VTP over 10.
Yeah, that VT equals VTP over 10 T to the TI, right? That tells you how much water's in the aquifer. So how would you use that to figure out the recharge between recession 1 and 2? Take a break, think about it. We'll finish it up after break, okay?